right? Oh, wait, I didn't take attendance. I got to pause this. Darn. Gosh. Yeah. So today is it's February. How exciting. Yeah. 63 and 3/4. Huh? Well, look at how many we have done.
We only have 64 more days of you.
Sorry.
Is this our last class?
More than likely. Yeah. Unless you go on and there's one more, but I don't want to talk about that right now. So let's get to it. Today we are going to learn how to graph quadratics. And unless they let me have you for like 6 hours, there's no way I could do this in a day. So I can get the introductory portion done today, which is really the worst of it all. I think it's always the worst part. Like when you first learn something, it's so awkward and clunky. And then we'll get practice, and then we're going to move over to a different format of equation, which you'll fall in love with right away because it's so easy. And then the final push is for us to take the way they look today and use completing the square to convert them into the way we like better. So it's kind of a journey to get to where we need to be. So today you'll probably find this one, when you look back on all this in a couple of weeks, you'll think this was probably the most annoying thing we had to do. So when you graph a quadratic equation or a quadratic function, you will always, and I never take that word lightly, you will always get a shape called a parabola. Make sure you put the emphasis on the right syllable. It's parabola and not like parabola. It's interesting if you change and you use it more like as an adjective and talk about something in its parabolic state, then you do put the emphasis on the first A. Like it becomes parabolic as opposed to parabola. So not that it really matters. But anyways, like if I just went over to Desmos and just randomly typed in anything that has an x squared in it. So like if I just type in y equals like x squared minus 4x plus 5. Boom, look. I mean, and I don't remember if we talk much about this in Algebra 1, but that's what a parabola looks like. And as you'll see today and over the next couple of weeks, some parabolas open upwards like a bowl. Some parabolas open downwards like an arch. Some parabolas are really skinny. So that means that they open a lot tighter, right? And some are really fat and they open more like a kitchen bowl. So that's kind of the goal for today, is to get you out of here so that you can accomplish a couple major things. Number one, mission number one, first part of the lesson is, can you find that point at the very bottom or top? Do you guys know what that point at the very bottom would be called? It's kind of a geometry word. Yeah, it's a vertex. It's like in a geometric shape, how like the corner of a polygon is called a vertex, right? The vertex of a parabola kind of feels the same. It's the point from which the parabola essentially spawns. So like throughout the day, as we graph parabolas, we're going to start with the vertex. That's your money spot. Like you almost never want to come at a parabola with other points. Like you want to spawn from the vertex, and then I'll show you mathematically, once you find the vertex, how to structurally construct the rest of the frame of it. So mission number one today is, how do I find the vertex? Like numerically, you could look at this graph right here and just eyeball it and see that the vertex is at the point 2, 1. The question is, how can I look at an equation like this, if you can read that over there, and make sense of how that equation lends itself to that vertex? So again, that's mission number one. And then mission number two is to identify how the structure changes. So like, let me just make up a parabola like negative 1/5 of x squared plus 4x minus 11. If I zoom out on that, then you can see this parabola. But once we cross the bridge of how do we find the vertex, like you can see this vertex is at 10, 9. Then we have a different question, like look at the different characteristics between the purple graph and the black graph. Not going to talk down to you and ask you, you can obviously see that the black graph opens in a different direction and that it's fatter. So you're all very bright people. What do you think caused it to open upside down? Just one negative, right? There's only a negative. The only negative that affects the structure of the graph is the one that's in the front. Like any other negatives have they're just going to move it around. But the negative that makes it flip over is the one that's attached to the beginning. And what do you think chunked it up? The fraction. Right. So that's the goal for today is operation mission number 1. Let's learn just how to find the vertex. To heck with the structure. How do I find the spawning point? And then mission number 2 is how can I now understand how to build the graph once I get to the vertex. The vertex is like our home base. Do you remember when we graphed lines in algebra 1, like y equals mx plus b? So I know it's been a long time, but like if I was teaching you algebra 1 and I did like 2/3 x, I don't know, minus 4. If this were an algebra 1 class, we would study this line and I would try to teach you that there's a starting point. I used to call it a home base. It's probably fresher in you ninth graders, it's probably fresher in your mind. So the home base on this problem would be down 4. And you can see that that comes from there. Kind of remember that? And then the slope is 2/3. So you could see that the graph goes from here, the home base, and then I go up 2, right 3. Boom, that's how we graph lines. So this kind of feels the same. There's a starting point and then a where do I go? Good, got it? All right. So the first graph we want to study is this one. And this is it's called, well, let's write it down first. This is we call this the parent function. I'll be honest, we used to call it the mother function, and that over time started to, I think mathematicians decided they were tired of the chuckles that induced because it sounds like you're going to say something else when you say mother function. So over time, it's sort of evolved and people don't call it that anymore. We call it the parent function. And every family of graphs has a parent function. And the family that we're going to talk about are quadratics. So this is the one upon which all other quadratics are based. And so the first thing I want to show you is what he looks like. And so if I just graph x squared, and you, by the way, that's most, like you'll use it sometimes. You don't have to type in y unless you want to. It doesn't care. So this is the parent function for quadratics. And where do you notice the vertex is at? Right. So that if we don't have occasion to move it, then the parent function is situated at 0, 0, right? Now, as I move around, like you saw in that previous example, if I start tinkering with it, if I put like x squared, like this out, plus 3x, my bad. Do you see how the vertex moved? And then I can give it another move if I put a number at the end, like here it goes, plus, poof, he moved again. So when you start adding some other things in different places, the vertex is going to have a little walkabout and go someplace else. So that's the goal here. So anyways, the parent function is y equals x squared. And let's talk about how to find a vertex. In fact, I'm going to call an audible on myself. I want to talk about one more thing. I'm going to go out of my own order here because I think that this is a good time to try to get this stuck in your head. So in your notes, I'm gonna help you add this into your notes. But if you listen really closely now for about 3 minutes, your life's going to be a lot better for a few days. So here it goes. The way I build the structure of the graph is once I know where the location of the vertex is, I want you to study with me where the next points are. So if I leave, I'm going to use a big fat red pen for this. So the vertex we all agree is right there, correct? But I want you to notice that I go, and I don't, sometimes I'm really tight on everyone has to say right and left. I'm going to say out 1 because out to me feels like I'm leaving and I can go left or I can go right. So if I go out 1, how far up do I have to go until I reattach? Good. So we just found a relationship of 1, 1. So let's head back to our other page and let's add this in. So for the default function, for the parent function, we have a relationship of out 1, up 1. And you'll see the pattern of why this works here in just a second. I'm going to head back over to Desmos now, and I'm going to switch colors, I guess. I'll switch to like purple and go back to fatty pen. If I go out 2, how far up do I have to go to find graphy? Very good, 4. If I go out 2, I have to go all the way up 4 before I can say that I've reattached with my graph. You see that? Okay, so we're going to head back. We are. Mhm. And so we can also now add to our notes that on a basic quadratic, if I go out 2, I have to go up 4. And yeah, that connection, you probably already made it, is that, yes, I'm just, well, here it goes. Wait for it, key to the yellow pen, I'm squaring it, right? I mean, that's how a function works, is the function dictates what you do. And so if the function says I'm x squared, then everything we do with x gets squared. So you know where this is headed. If I go back to Desmos, if I go out 3, I would go up 9, correct? And we can prove it. I mean, I need to erase these points, but I can just show you if I go out 3. So I'm right here. You can I'm sorry the numbers are so small, but there's out 3. And look at that. Sure as shooting, I got to go up 9 and I reattach with the graph. And that's true on the left side and the right side. All parabolas have this symmetry. Okay, there's a line that runs up the middle called the axis of symmetry, and all the points that we build are the same on the left as they are on the right. So really, you only have to build one side, and then the other side kind of falls into place, right? So let's add this. Let's go back to the other page. If we go out 3, we go up 9. You agree? What if we go out 4? Yep. And we do enter a point where it becomes like it's not really practical, a lot of graphs, until you start changing scale. It's hard on a piece of graph paper to go up 16. And then you get to out 5. And we'll probably stop at this point, but you get the idea. How far up would I have to go? Right. So that is the nature of a parabola. Like that's, and what I need you to really do is memorize the numbers that I'm going to circle in purple. 1 goes with 1. 2 goes with 4. 3 goes with 9. 4 goes with 16. 5 goes with 25. And we'll come back to this in the second part of the lesson. I just wanted to get that out while I had the graph up there. So we clear? And of course, if the graph opened upside down, those numbers don't change just because it's upside down. What would change is you would go out 1 and down 1 and out 2 and down 4. Like the structure is just flipped over. Same thing. Good on that? All right. So now let's figure out how to find a vertex. So finding the vertex is a formula. You know how you get a formula in math and you want to keep it close by, like the quadratic formula when you first learn it, you want that sucker in a box. You're going to want this formula. This is your guy. X equals the opposite of B divided by 2A. And the very, 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 very mathematically observant among us would notice that that's just a castrated quadratic formula. Did you see it? The quadratic formula is negative B plus or minus a bunch of crap divided by 2A, and that's not happenstance or coincidence. But if we do take that quadratic formula and cut off all the square root of b squared minus 4ac stuff, we're left with an x value that will always be the perfect dead center of the parabola. So this is the magic trick for finding the vertex. So having said that, let's try out a function like this one. So C is, I never want to say it doesn't matter, but for this formula, I don't really care about the 10. Like he'll come in later, but right now, if I'm just on a mission to find the vertex, I need A and I need B. That's all. And so in this quadratic, what's A? Just 1, right? Remember just the numbers. And what's B? Just the 6, right? So if I pop those numbers into the formula, and how people mess this up is one of those things I'll take with me to retirement, never understanding. It literally says take the opposite of B and then divide it by double A. Right? So what is the opposite of B? So I'm going to put negative 6 on the top. And then the bottom says to just double A. What's double 1? And what is negative 6 divided by 2? Good. So here is your vertex right there. I probably should have changed colors for that. Here, I'll put a box around it so it really stands out. This is your vertex. Now, obviously, what's missing? Why? Like a vertex isn't a vertex if it's just one number. If I said, hey, Seth, the vertex is at -3, he's going to look at me like, yeah, you're going to have to do, yeah, you're going to have to do better than that, Holmes. Like it's a start. It tells me that to get to the vertex, I have to go left 3. Okay, great. But then the question is like, well, now where do you want me to go? So that's where a little bit of basic algebra comes into play. And as has always been the case since like 7th or 8th grade, if you are working on an XY problem and you know one of them, how do you find the other? You plug it back in. So I just take this -3, follow the green arrow, and I just put it right back into that equation. And, you know, again, those of us whose basic skills are weak will suffer, and that is what it is. Sucks, right? So if I change both of the x's, I'm going to circle them, this one and this one. If I change them, so we're going to take both of the x's and change them both into -3s. And then as always, we just, bam, we hope the math goes well. So right here in the first purple jelly bean shape or whatever that is, what's -3 squared? Right, yeah. Hopefully the days of us saying things like -9 are far behind us. And then for the second little purple eggy thing, what is 6 times -3? Yeah, -18. And then we're going to, there's Mr. C. Remember I said we didn't need him, but we need him now because he's going to complete our vertex for us. And what is negative, or what is 9 minus 18? And what's -9 plus 10? So there's your vertex. And so when we think about the vertex, it's like the formula gives us the x, and then a little bit of elbow grease gives us the y. So let's take a look at this guy over on Desmos, x squared plus 6x plus 10. So x squared plus 6x plus 10. And as we predicted, there's the vertex at -3. Okay, so that is mission number 1. And this process is going to get infinitely more difficult as fractions and uncooperative numbers become involved. Okay, any questions on just the general basic of how to find the vertex? All right, let's try something a little bit tougher. And by the way, you'll also see this notation. Maybe I should go back and forth so you don't think it's a big deal. F of x notation is just when someone wants to specify that they're using it as a function. Y equals is more just kind of a basic y and x thing, but they mean the same. So I struggled with that when I was a kid. So f of x equals y equals, it's all kind of the same. So let's do 1/2 of x squared minus 2x plus 3. So this is where the struggle bus really starts to pull up to the curb, and you just have to decide if you want to get on it or just wave it by. What's A? 1/2. And what's B? -2. So faithful application of the formula tells me that I'm going to do the opposite of B divided by 2A. What is the opposite of B? And I'm going to put 2 over. And this is where some people look at that and just go 1. Some people go, I don't know how to do that. So listen, when I say to do double A, what I mean at a very grade school level is this, to do 2 times A. That's what it looks like. And remember what someone not me taught you is that to multiply 2 fractions, you take the 2 and you put it over 1. And then if you're going really old school, you just multiply those together. 2 over 2 equals 1. In a more perfect world, we don't need to go through all this rigmarole. You just look at 2.5 and then you just know that they equal 1, right? So what is 2 divided by 1? Good. So our vertex is currently all we know at 2 comma something. Now, if we put 2 in place of these little green circles, go. Order of operations demands that we do 2 squared first. What's 2 squared? What's half of 4? So we have 2 minus, and then in the second green circle, put a 2 there. What's minus 2 times 2 is just 4, right? So I already got the minus there. So 2 minus 4, then copy the plus 3. What's 2 minus 4? And then what's -2 plus 3? There you go. So that is the fine art of finding a vertex. And it can get even more annoying when there are even less cooperative fractions involved. And then we'll get over to the structure part of this. So you have a question or you just stretching? Okay. It multiplied by 2. Our Are you talking about this at the beginning? This? That's part of the structure. It was my A value and I used it for the bottom. Well, I did negative B over 2A. And then so this box right here is 2 times A, and this box is also 2 times A. So A, huh?
When we filled in the x's with the two, we did two squared, just fill one half of four two.
We use the half again. We just, once we plug it into the formula, we're kind of done with it for a minute. Let's do another one. I think you'll answer your own question. Not sure, but I hope. Let's do 3/4 of x squared plus 9x minus 11. Let's find the vertex. This will be our last example of this, and then I'm flipping the note card over, and we're going to talk about the structure. So then we'll put it all together, and then you'll probably just have a nice big fat work day on Monday because I'm gobbling up most of your time here today. It's all good. It's for a good cause. So what's A? So yeah, sorry I didn't put like y equals. Yeah, so A equals 3/4. I like to write them down. I've always done that. You know that, like with quadratic formula, whatever. What's B? Right, okay. So let's do this. So we're gonna do the opposite of B, which is -9 divided by 2A. Now there's a math problem here. So I need to do 2 times 3/4. Right. And again, some of you, I feel great about it. I wish everybody did, but some of you just look right at that and go, it's 3/2. So how do we attack it? It's up to you. Like, I don't really care how you get there, but like Bryce probably did the 2 and the 3 and got 6, like multiplied those and got 6. And then he just put the 4 on the bottom because there's a 1 next under the 2. And then did I guess correctly, or did you reduce? Like you can reduce before you multiply. So like this 2 and this 4 that I just circled in yellow, you could reduce early to 1 and 2. Like, I just don't, I hope that's not the crux of the conversation is how did I get that? Like, that's a really basic concept. So where it says 2 times A, I did 2 times 3/4, and the answer is 3/2. Are you with me? If you can get over this, then I don't think there's a lot of challenge because the rest is just pretty, I hope, pretty basic. So now I got a copy dot flop. So what I have now for my negative B over 2A is I have negative B divided by 2A. You see, right? I've already done that math. And how do we divide a fraction again? Copy dot flop. So we're going to make it -9 over 1 times 2 over 3. And again, you can calculate that at your own pace. What does that equal? -6 is perfect. So my vertex is at -6 comma something. You see, it gets a little harder. The math doesn't, like the expectation, the formula doesn't change, but the basics become a little less basic-y. And now to find the actual vertex, remember everything that I see on the board right now, or that you used to see before I vandalized it, that was all just the work to find the X. And now the Y is going up to these little green circles and putting -6s in their place. So if you do this first purple oval, what is -6 squared? And here we go again, basic skills. You didn't know this was going to be a basic skills day. You got to do 3/4 of 36. Right. And again, I love that you can do that quickly. This is not a good time to multiply and reduce, right? The mathematicians understand there's a time to go across and reduce later. This is not one. It's better in this case to take 36 divided by 4, which is 9, and then take 9 times 3, which is 27, right? And now let's put -6 also in place of the second green circle. What's 9 times -6? -54. Take away 11. And this is not one I'd probably want you to graph, but I was just making it up. What's 27 minus 54? -27 minus 11 is, so this would have a vertex way down in quadrant 3, left 6, down 38. All right, you guys good on the process, the math? All right, let's talk about the structure. And I just want to get this all out of the way today. So consider this. For this particular portion of the lesson, I am not going to put any linear and constant terms. I don't want there to be any distraction in that regard. I'm going to just take this and I'm going to head over to Desmos and I'm going to graph two things. There's x squared. And in Desmos, you can graph multiple things and it even color codes them for you, which is crazy cool. It's perfect in my line of work. So now I'm going to graph 2x squared. And the darker graph is the one I just graphed. I'm sorry to ask this, but what do you notice? It's thinner. And what causes a graph to be thinner is that it grows at a quicker rate. This time, I'm going to use my big red dots again, because this is a perfect time for the big red dots, if ever there was a perfect time for the big red dots. So I'm going to focus on the dark graph. When I go out 1, how far up do I have to go to get to the dark graph? Up 2. And you'll notice, if you're paying attention, that it used to be up 1, but now it's up 2. Interesting. If I go out 2, my big red dots are going to fail me now. If I go out 2, how far up do I have to go to get to the graph? Correct. And you might have already solved the riddle. How we double, we take whatever the OGs were, and those OGs are huge. Those of you that take the time to memorize the numbers 1, 4, 9, 16, 25, like they're just squares, all you have to do is take those original numbers and modify them based on the number in the front. So if I know that my front number is a 2, then I just take and say, instead of going out 1, up 1, I'm going to go out 1 and up double 1. And instead of going out 2 and up 4, I'm going to go out 2 and up double 4. If I go out 3, how far up would I go? Normally 9, 18 for us. If I went out 4, how far up would I go? 32, because that's double 16. If I went out 5, how far up would I go? Because that's double 25. And it works the other way too. So if I had something like, let's flip it on its head. Let's do it the other way. Let's say I did 1/2 of x squared. You wanna guess? I mean, what do you think is going to happen to the graph? It's going to be wider. It's going to be fatter, right? And so if I get rid of this, and let me change this to 1/2 of x squared, and sure as shooting, like Seth said, look, it's a fatty. And the reason it's a fatty is because now when I go out 1, how far up do I go? 1/2 of 1, which is 1/2. If I go out 2, how far up do I go? 1/2 of 4, 2. You just got to keep hitting those original numbers. The 1, 4, 9, 16, 25, 36. You just keep abusing those numbers and you build subsequent points on your parabola based on a value, what we call a scalar, a multiplication scalar, right? So I modify. If I go now and, what's up, buddy?
Way different if we did like 3/2.
Well, it would, let's get some numbers down and let's address that. We'll let Desmos answer that for us. But for now, if I'm on this graph now, if I go out 1, I go up 1/2 of 1, which is 1/2. If I go out 2, I go up 1/2 of 4, which is 2. If I go out 3, I go up 1/2 of 9, which is, not scared, 4.5. If I go out 4, how far up do I go? Do the math, right? 1/2 of 16. Always say, what would I do? If there weren't this stupid number in the front, I know I would go out 4 and up 16. So I take that 16 and I multiply it by the number in front. 1/2 of 16 is 8. If I went out 5, I say I'd normally go up 25. What am I going to go up? 12.5. If I go out 6, what would I go up? Normally 36. 1/2 of 36 is 18, and so on and so forth. Got it? So your structure is modified only by one thing. Your structure has nothing to do with the other terms in the equation. It's all about the number that's in front of your quadratic term. He's the only one that has any say in physically what the graph looks like. The other guys play a hand in where do I go to make the graph, right? They're like the directions to the build site. But once you get to the build site, the blueprint, how to build it, that's all dictated by the guy in the front. Good. What do you think? Oh, your question. You had a question. What happens if I put something in front like 3/2? That's a good question. Let's take a look at that. So normally And you could think of it as like a 1.5, 1.5 scalar if you want, but let's just make it very mathy. Normally, if I go out 1, how far up would I go? How far up would I normally go? 1. Always say like normal 1. 1 would be the default, but if I take 1 and multiply it by 3/2, I get. So if I go out 1, I'm going to go up 1.5. Normally, answer this. If I went out 2, normally, how far up would I go? But I need to do 3/2 times 4, which again, you should be quick at this, is 6. Quick, quick, quick. If I go out 3, normally I would go up 9. So I have to do a little math. What's 3/2 times 9? 27/2, also known as 13.5, 13.5. If I go out 4, normally I would go up, but I need to do 3/2 times 16, and that is 24. Right? Does that answer your question there, Swaggy B? Okay. So you're going to find yourself doing a lot of basic math. If you don't like it, well, too bad. So sad. So the last part of this, we got about 10 minutes ish, is I want to wrap it up with just let's put it all together and let's just make a graph. Let's just talk about, can I just make a graph from scratch? So our first one, and I've got a bunch of these. I doubt I have time for them all. Let's give it a go. So to conclude this lecture today, we want to now have like a flow chart, a step-by-step guide of do this, then do this, then do this, then do this. In step 1, without question, will always be to find the vertex. We clear? You're not going anywhere until at least you know how to get to the build site. And so what's our formula again for the vertex? Perfect. Opposite B over 2A. Just get that stuck. Just, boom, there it is. You use it every time, every time. What's A? What's B? Good. What's the opposite of B? And what is 2 times 1/2? 1. And what is -2 over 1? Okay, so I'm going to switch colors now. This is important. In yellow, the vertex has an x-coordinate of -2. That's huge. And how are we going to conclude the vertex or complete it? What do we need? Plug it in. We need the y. So we're going to take -2 and we're going to put it right there. And we're also going to put it right there. And we're just going to hope and pray that things don't go south. So what is -2 squared? What is 1/2 of 4? So we have 2. That's the first part. Now, the second yellow arrow, the one further to the right, if I put -2 right there, there's a white arrow to join him. What's 2 times -2? So I have -4 plus 3. What's 2 minus 4? What's -2 plus 3? We now know that's sweet prized possession, the vertex. Clear? So if we were doing this on a piece of graph paper, let me add in some graphy stuff here. We would now know that the vertex is at the point -2, 1. So the first thing you do when you're making a graph is you head over to that point and you put a dot there. So I'm going to go left 2, up 1. There it is. That's huge. That's my jumping off point. Now, structurally, this is where we put it all together. By the way, at this point in time, watch this. Super vandalism incoming. At this point in the problem, none of that matters ever again, right? We found the build site. Now, all that matters is 1/2 says it's my moment to shine. I'm going to tell you how to build a graph. First off, does this graph open up like a bowl or down like an arch? Up like a bowl because a 1/2 is positive, right? And let's talk about defaults here. Let's see if you get this. Normally, I would go out 1, up 1. I'm going to go out 1, up what? 1/2. The modifier tells me to only go halfway to 1. Normally, I would go out 2 and up 4. What will I go up? 1/2 of 4, also known as 2. This is how you construct a parabola. Find your home base and then use the structure builder number to find your points. Normally, I'd go out 3 and up 9. Not me. What am I going to go up? 4.5. 1, 2, 3, 4.5. Bless you. Normally, I would go out 4 and up 16. What am I going to go up? 8 because that's half of 16. So I'm going to go at 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. And every time you do this, like in your assignment, every problem has like a critical mass where like you can't fit anymore. And I feel like I'm probably at about that. And then to me is the hardest part is graphing the parabola. And this is where you just have to be really delicate with your pencil and try to make it look like a bowl. And what I do is a lot of times I just very lightly sketch, and you will find this, unless you're a very artistic person. I've been doing this almost 30 years and I still struggle to graph parabolas, like 30 years. So here's some things that are not allowed. If you make a graph that looks like this, I'm going to give you points off. We clear? Like that's not a threat. I'm just telling you, I can't have you graphing absolute value functions here. And here are some other ways to lose points. Because I know you should be interested. Like, what are some things I could do that would cause me to be like wrong? Here's one. When you make a graph that goes up like this and arrows out, parabolas do not do that. I will take points off. You listening? And then number 2 thing that you can do to lose points is have the parabola double back on itself. To be a function, you cannot double back on yourself. So if you do a really nice parabola and then you just bail out and go like this, 100% of the time, you're losing points. So parabolas are really hard to draw. You'll find once you get the math, you're like, the hardest part is making it look like something other than crap. But you can't wing out like that. You can't come back in like a horseshoe, and it can't be straight. So it takes some practice. Good. All right, let's do another one. I don't have time for a lot, but let's do, this one's pretty middle of the road. Let's do this. This is a nice kind of average difficulty one. So step 1 is figure out what A and B are. What's A? -2, what's B? Good. And then we just got to embrace that formula. What's the opposite of B? 12. What's 2 times A? What's 12 divided by -4? So our vertex is definitively at -3, comma something. And how do we find the something? We plug it back in. So we're going to take -3 and put it in place of both of those yellow X's. And we just assume this is going to go well. What's -3 squared? 9. What's -2 times 9? -18. And then in this second portion where the big yellow oval is, what's -12 times -3? +36. What's -18 plus 36? And what's 18 minus 14? There's your vertex. All right. So on a piece of graph paper, we would, let me bring my graph paper back. Oh, I'm so sorry about that. Oh, geez, Louise. So we know the structure, we know the builder. And if you could just kindly give me 1 more minute of your life, we might go up to the bell, but that's the worst thing that happens all day. It'll be a good day. So just give me 1 more minute, please. Let's go graph our vertex, -3, 4. That means to go left 3, of course, and up 4. So 1, 2, 3, 1, 2, 3, 4. Describe for me the structure of this graph. Talk about him. What does he do? He opens down like an arch. Very good. And how steep is he? Like when I go out 1, what will I go down? 2, because the modifier in front says to double all of your y's. Never mess with your x's. Always go out 1, out 2. Don't ever mess with your x's. Just mess with your y's. If I go out 2, how far down am I going to go? I would go down 4, but I'm going down 8 because the modifier says I got to double 1, 2, 3, 4, 5, 6, 7, 8. And that would be enough. We're going to run out of space. Recording over, class over. Monday, we'll probably freshen up and then we'll have a work day. Bye.